May 2018, deep beneath the Indian Ocean, a swarm of mysterious earthquakes signals the birth of a colossal underwater volcano, erupting at hundreds of cubic meters of lava per second. Its scale is invisible but world-changing. Scientists now suspect 80% of volcanic action is hidden underwater, reshaping life and our technology. But if volcanoes control the foundations of civilization, what else do we owe to their secret power? The answers begin in darkness, where few have dared to look. A sudden burst of seismic activity rattled Mayotte in May 2018. Earthquakes, some strong enough to be felt by residents, began shaking the island, an unusual event for a region with no known history of major volcanic unrest. Scientists from the French Research Institute responded quickly, deploying a network of land-based seismometers and ocean-bottom sensors. Their instruments traced the source of the tremors to a spot 50 kilometers offshore, nearly 3,500 meters beneath the surface. GPS data revealed that Mayotte itself was moving. The island shifted 24 centimeters east and dropped 19 centimeters, a sign of deep geological change underway. Aboard the Marion Dufresne research vessel, teams mapped the seafloor using high-resolution sonar. The data revealed a massive new volcanic cone, 800 meters tall, that had not existed a year before. This was the birth of Fani Mayotte, the largest underwater eruption ever observed in real time. Remotely operated vehicles captured footage of lava pouring out at rates exceeding 400 cubic meters per second, instantly cooling into bulbous glassy formations known as pillow lavas. Hydroacoustic instruments picked up the low-frequency tremors and the rise of volcanic plumes through the water column. Over the following months, more than 6 cubic kilometers of magma poured out, reshaping the seafloor and sending clouds of volcanic gas toward the surface. For the first time, scientists watched the creation of a new volcanic edifice from start to finish, using a combination of seismic records, bathymetric surveys, and direct visual confirmation. The Mayotte eruption exposed a hidden force at work beneath the oceans, one capable of moving entire islands and altering the map of the planet, all while remaining invisible to the naked eye. Stretching more than 65,000 kilometers around the planet, the mid-ocean ridge is Earth's largest volcanic system, a continuous mountain range hidden beneath the ocean's surface. Along these ridges, tectonic plates drift apart and molten rock from the mantle rises to fill the gap, creating new oceanic crust. This process is relentless, with magma cooling and solidifying into vast sheets of basalt, layer by layer, year after year. Most of this volcanic activity remains out of sight, buried under thousands of meters of water, but there are a handful of places where the ridge breaks through to daylight. Iceland stands out as the most dramatic example, a volcanic island straddling the mid-Atlantic ridge, fueled by both plate divergence and a powerful mantle plume. Yet the ridge also surfaces in places like the Azores and Jan Mayen, each a testament to the scale of Earth's planetary plumbing. Iceland's unique geology turns it into a natural laboratory for scientists studying the forces that shape the seafloor. Teams of geologists collect fresh lava samples from recent eruptions, analyzing their mineral content and chemical signatures in university labs. These studies reveal the composition of the mantle, the speed of tectonic spreading, and the complex mixing of magmas beneath the crust. By comparing Icelandic lavas with those dredged from the deep ridge, researchers can trace the origins of volcanic material and reconstruct the processes that build new continents over millions of years. This hidden system is not an exception, it is the rule. Every year, mid-ocean ridge volcanoes add more than 2 cubic kilometers of new rock to the planet's surface, quietly reshaping the seafloor on a global scale. The story of Mayotte is just one visible chapter in an ongoing planetary process, one that has been forging the world's continents and oceans since the dawn of geological time. In the year 939, the Eldgjá volcanic fissure in Iceland released 220 million tons of sulfur into the atmosphere. This eruption, one of the largest of the last 2 millennia, sent a dense veil of sulfate aerosols into the stratosphere. Ice core records from Greenland and Antarctica show a sharp spike in sulfate layers, while tree ring studies across Eurasia capture a sudden drop in summer growth. The result was a dramatic cooling. Average global temperatures fell by as much as half a degree Celsius, with some regions experiencing even greater drops for several years. Medieval chronicles from Ireland to China describe failed harvests, summer frost, and widespread hunger, all tracing back to the sulfur haze blocking sunlight. 1,000 years later, in 1991, Mount Pinatubo in the Philippines erupted with a force that injected 20 million tons of sulfur dioxide into the upper atmosphere. Satellite measurements tracked the resulting aerosol cloud as it circled the globe, raising the planet's aerosol optical depth and reflecting enough sunlight to lower global temperatures by about 0.5 degrees Celsius for nearly 2 years. Dendrochronology and modern climate models confirm the scale of these disruptions. Both Eldgia and Pinatubo stand as clear evidence. When volcanoes inject vast quantities of sulfur into the sky, Earth's climate responds on a planetary scale. In the late Bronze Age, a volcanic explosion tore apart the island of Santorini, unleashing an energy equivalent to 40 atomic bombs. The city of Akrotiri, once a thriving Minoan port, vanished beneath 20 meters of ash in a matter of hours. Homes, frescoes, and intricate plumbing systems were sealed away, preserved for millennia by the suffocating blanket. Greek archaeological service teams, decades later, uncovered entire streets frozen in time, evidence of a civilization caught mid-step. But the eruption's reach extended far beyond the Aegean. Winds carried volcanic ash south, settling over the Nile Delta. Egyptian records and modern stratigraphy reveal a sudden ecological shock. Red algae bloomed in the river, turning waters toxic. Crops failed, locusts swarmed, and livestock perished. The chain reaction devastated harvests and sparked famine, echoing through ancient texts and ecological records. Some scholars draw connections between these events and the biblical plagues, though the debate continues. What remains clear is that a single eruption could disrupt societies hundreds of kilometers apart, forcing people to adapt, migrate, or vanish while preserving a lost world beneath layers of volcanic memory. Around 200 BCE, central Mexico's landscape was shaken by a series of eruptions from Popocatépetl. Archaeological layers across the basin of Mexico capture abrupt changes. Villages were abandoned, fields were buried in ash, and a wave of migration helped seed the rise of Teotihuacan. Within a few centuries, this city became the largest in pre-Columbian America. Its obsidian workshops were fueled by volcanic glass from nearby flows. Far across the Mediterranean, islands like Pantelleria became regional hubs for another prized volcanic material, obsidian. Modern geoarchaeologists use trace element analysis to match obsidian blades found in Neolithic settlements to their volcanic sources. Artifacts from Pantelleria have turned up in coastal Tunisia and southern Italy. Evidence of ancient sea routes forged by the demand for sharp, durable volcanic glass. These exchanges reveal how eruptions not only forced people to move, but also knit distant communities together through trade. In southwestern Iceland, a team of engineers monitors the hum of turbines at the Svartsengi geothermal plant. Here, volcanic energy is harnessed on an industrial scale. Underground, magma heats vast aquifers, turning water into steam that rises through drilled wells. This steam spins generators, producing 75 megawatts of electricity, enough to power entire towns. The remaining heat is piped directly into homes and businesses, providing 190 megawatts of hot water for bathing and heating. For a nation of just 330,000 people, this system supplies the backbone of daily life. Decades of energy planning and innovation have transformed Iceland's volcanic landscape into a renewable powerhouse. Utility engineers and national planners now look to these volcanic reservoirs not as threats, but as reliable sources of clean, steady energy, proof that the heat beneath our feet can drive a modern society. On El Hierro, engineers and water managers rely on the volcanic landscape to survive drought. Forests planted along the island's peaks draw moisture from passing clouds, while ancient lava flows store rain deep underground. For generations, islanders have carved galleries, tunnels that stretch through solid basalt to reach these natural reservoirs. Water filtered through porous volcanic rock is collected and piped to every corner of the island, sustaining life in a place where rainfall is scarce. Thousands of kilometers away, Chilean geologists work atop the vast salt flats of the Atacama Desert, where volcanic activity over millions of years concentrated lithium-rich brines beneath the surface. Here, 350 shimmering pools stretch across an area the size of 2,400 football fields. Extracting lithium from these brines is a slow process, taking up to 16 months for the sun to evaporate the water and leave behind the mineral that powers cell phones and electric cars. From island aquifers to global battery supply chains, volcanic gifts shape the essentials of modern life. Every smartphone, electric car, and city built on fertile volcanic soil owes its existence to forces we still cannot fully control. As demand for critical minerals and renewable energy surges, our future remains tied to volcanic power. These mountains shape tomorrow, whether we are ready or not. Subscribe for more untold connections.